I'm going to talk next about profiling deep learning. I'm going to talk about TensorFlow. We'll follow and talk about PyTorch. There's some interactive exercises you can follow along with in the SDL workshop repository. So you go to this top folder, and then profiling deep learning, and then TensorFlow. And additionally, you should feel free to run them on the systems as well. Zoom in here. So I hope this is large enough to read, and tell me if it's not. But I'm running, I have a compute node on Polaris. You don't need Jupyter for this one, you can just follow along. So in this tutorial, we're going to profile a GAN network, a generative adversarial network. If you're not familiar with these networks, for this tutorial, it doesn't matter. Let's just say that this is a machine learning training script, including data ingestion, network optimizations, training loop, all of the typical things. I picked a GAN because it's slightly more complex than some of the other networks, and there's some extra steps to worry about when you're trying to optimize it. The output of the network would look something like this when you train it. This is kind of a grid of these generated images. So it's basically building off of the MNIST data set. These are the handwritten digits. At least some of them are. Some of them are mostly smears. And that's okay. For this network, this is just, an example to work with for profiling. You can find the original script here, train-gan.py, and it uses the conda module from September. So if you're following along, just do module load that conda and conda activate. And just to show you the original script, if you run it, you'll see after a couple of TensorFlow printouts, it'll start doing its training loop, and it's going to average about 300 images per second for each iteration. So that means it takes 300 images, does the GAN training loop, and is ready for the next one. The latency for the step time is about 0.4 seconds, so less than half a second per step. And this, at first glance, it can be hard to say, is this good? Is this bad? That's one of the nice things about profilers. You can actually get into that and determine good performance or bad. And then the optimized version, which hopefully we'll get to by the end of this 20 minutes. I'll run it. It'll do a little bit more printouts at the beginning. Instead of 300 images per second, it's going to be running at about 170,000 images per second. So that's about a 600 times improvement in speed. And in fact, in the time it takes the first one to do a single epoch, this script will completely finish the training. There it goes. So the time per step is actually down by a factor of 10, and the total throughput is up significantly. So how do we get this? I'll walk through the whole process of how I optimized that first script to get to this. But first, let me just take a look at the script and show you what the original one looks like. So you can find it on GitHub, of course. It's not a data parallel script, though we talked about that this morning. This runs on a single GPU. This function configures the output that's actually printing out the throughput. In the GAN, there's two models. There's a discriminator and a classifier. These are built just off of tf.keras.model layers and functions. So if you're used to machine learning, this should not be a big shock for how this network is built. It has a call function. The generator is very similar, built with the same tools with the call function as well. And then there's this function for computing the loss between labels and targets. If you've done some of the earlier exercises with the sigmoid cross entropy with logits, this is also familiar. This function reads in the MNIST data set, which is used for this script. And then here's the forward pass function, which is where you build most of your machine learning training loop. It takes in these two models and the batch size and the input size for how much you want to feed the generator of just random data. And it goes through the whole training forward pass until you get to the loss. So what that does is it gets a real batch of data, creates some input noise for the generator, and then it predicts based on the discriminator what the prediction was on real data and on fake data. These steps here are computing labels to feed in for the final loss calculation. And then it computes the loss for the models. It actually calls this compute loss function 3 times, twice for the discriminator, once on real data and once for fake data, and once for the generator. The total loss is then computed for the discriminator and the generator, and it gets returned. The training loop, on the other hand, just takes some number of epochs, pulls a batch for however many epoch steps you want to take, and it will go through the 2 networks, compute the loss with the forward pass, and then it applies the gradients from this gradient tape technique from TensorFlow, applies the gradients, and it repeats. And the train GAN function down here at the end is just building the networks initially. So you build the generator, build the discriminator, call your training loop, and go. And that's the whole script. The first step to profiling, if you're using a Python workload, is, in my opinion, always line profiler. This is a Python built-in tool. You can install it with pip. You could do pip install line profiler. If you're using the Conda module, it's pre-installed already. So you can check, just run which kernel prof, that's the executable. When you use line profiler, if you go into this line profiler folder, you'll see there's this repeated script train gan.py. By the way, a lot of these scripts are copy pasted with changes for profiling. Definitely not the ideal software development technique, but hopefully you can find some of the instrumentation parts already done for you. But if you look at this train gan.py script, this has function decorators. It should. It's easier to find them. There it is. Profile, sorry, it's a function decorator. I put it on the training loop. I put it on the forward pass, and I put it on the last function here, train gan. When you run the profiling tool, so I prof, and then I say -L for line profiling. This kern prof call replaces Python when you do this, and then I can say train y. It will run for a while, and any function that's decorated with that profile function decorator, line profiler will track that function, and it will take a note of how often you call that function, and for each line in that function, how often that line is called and how long it takes. And you can get some summary metrics at the end. So I'll hit Control-C. It writes the output to this file here. It's usually the name of your script, .lprof at the end. And then you can look at that with Python -m and profiler in your script, and you get something like this. So this is showing me the function contents line by line, which are the functions that I asked it to profile. So the first one is this train gan function. It only came through here once because that's the sort of master loop, not even loop master setup function. And so everything in here is a one-time cost. It's not necessarily great for figuring out how to improve the speed of your train loop, but you can at least see what's taking the longest. Most of the time is spent in train loop, which is kind of where we expect it, and about 10% each in building these networks. So that's fine. The next place to look is train loop, which you can see here. It tells you what the function is and how much time is spent. And again, you get this line by line breakdown of what percentage of your time is spent on each line, as well as how much per hit on average, and how many hits it comes. So this forward pass function got 106 hits, and it took 88% of the total time. So no matter what else is happening in this function, the forward pass is dominant. Everything else you do would only speed up your code by 10%, even if you optimize everything to take almost no time. So let's look at this forward pass function up here. Again, same deal. Now we see 89% of our time is spent right here on this line. Real data equals fetch, real batch, and then telling it the batch size. So take a look at that function. There it is. Okay, fetch real batch. it's calling train x test equals get data set, and then it picks a selection of the data set and returns those images. We just saw from Taylor the importance of doing your data loading properly. So it's immediately apparent that reloading the data set every time using this call up here is not optimal. So 90% of our time is spent in these two functions, which we could very easily fix. If you look at this function, this script, train gan IO fix, this now loads the entire data set right up at the beginning. So it's a global, and it puts it in a TensorFlow data set. And then when you call down here, fetch real batch, oops. It's just using the global variables for xtrain, and it returns something reading off of the global. There's obviously better ways to do this than this. I just wanted to highlight this is one way to fix that, to find and fix that IO error. I have it instrumented again, so I can do turn prof -l train gan IO fix, and it will run again and as well compute this line by line breakdown. I'll just give it a second here. We should see about a 10x speed up. There it is, 1500 images per second instead of 300. So it's 5x. And if I do the output of the line by line profiling, interesting. There we go. I didn't type the full file name. Okay, just recapping here. Creation of the models is still, a significant chunk, but it's largely irrelevant. We're now down to 71% of our time in the training loop. Inside this train loop function, we've got now 46% of time in the forward pass and 33% of the time in the gradients and 18% updating the weights. And again, up here, this is the forward pass call. 30% of that is using our generator, and almost another 50% is using our discriminator. So this is telling us that by and large, most of the time in the script is spent doing TensorFlow calls. So following the networks, computing the loss, updating the gradients, and everything else is kind of peripheral. So the next step for that is, if you're using TensorFlow, is to use TF functions. So if you come into the TF function area, let me put this on GitHub. I think it's easier to look at. This is the same script with the IO fix, but now I've taken many of the functions and I've instrumented them with this TF function line. And what that's doing is it's JIT compiling these functions. So it does a trace for a graph, and it no longer comes back to Python after the first call. So the first time your network calls this call function, all of this will happen in Python, and it'll keep track of everything it does. And then as long as you call it again with the same shape inputs, it won't come back to Python. It'll just use the graph that it already has, and that can give you a pretty significant speed up. I also do TF function on some of these other functions, not just the models. So I compute the loss with the TF function, and I do the forward pass in the TF function too. So that's actually taking the entire forward pass and writing it into the graph. I encourage you, if you're interested in seeing how that happens, to do a comparison of this forward pass function and the one in the previous folder. A number of the NumPy calls here had to be replaced with TensorFlow calls. And the reason for that is when you're doing a tracing, when you call the things outside of TensorFlow, it appears as a constant to the TensorFlow tracer. So that's not necessarily what you want. Instead, you might want to have TensorFlow calls that will get included in the graph. I do the same thing down here with the train iteration. The step that included doing the forward pass, getting the variables, computing the gradients based on the loss, applying the gradients, and then updating the model all gets put into this private function train iteration, which goes through first for the generator, second for the discriminator, and then it updates it all. so that the training loop itself, which is actually running in Python, just calls this train iteration once per train iteration. And it will run until the discriminator loss hits some lower floor. And this is arbitrary. When I do this now, I can do Python train and IO fix. Things should run even faster. There we go. We're now at 87,000 images per second. Once you've gotten to this point, many things are TensorFlow graphs instead of just Python functions. And the way to profile those is with the TensorFlow profile. So we saw a little bit of that in the previous session. You can take this script here. Here it is. Train GAN TF function XLA. And I've added XLA compilation tools to this one too. So it doesn't change your model at all. It just adds an extra compilation step for TensorFlow and makes it go faster. I'll just show you the results here because you can run this and get the results yourself and look at them. Most of what we see is that the time per step is very consistent. It's almost entirely device compute. And of that device compute, most of the op placement is on the host. Okay, what's that coming from? That's actually the compilation step. So if you run this for much, much longer, you'll see this host fraction drop and a device fraction increase. Very little time is spent on eager execution. That tells us that most of it's in graph execution. And it shows us the most time-consuming operations. So some of these XLA compile, you should basically ignore in terms of profiling. That's just the cost of compilation. And then XLA run tells you what's actually taking forever. And you can't really tell what this is doing. Cluster _4_1 XLA run. Who knows? That's the one downside of XLA. Looking over at the kernel stats, though, we do see in the end that it's the things that it's compiling are UDNN, grouped, direct kernel. These are convolutions. So we know that this is a convolution op that it's compiling. So cluster _4_1 must be running a convolution kernel. And the last thing that I'll show on this page is that it must be cut off here. Here we go. Only 0.0% of device computation is 16-bit. So we have no reduced precision, and we can go much faster with reduced precision. So the next step to improving things is to use reduced precision. So that's over here. And that gets you up to this 162,000 images per second. When you just add this one line and switch all the float 32 to float 16s, and you can go almost twice as fast out of the box. And when you run the profile again, we no longer have that complaint that it's mostly float 32, and it shows us the device compute precisions more than half of it's in 16-bit. So that's great. The remaining calls that aren't in reduced precision, and you can see them because the op is not using TensorFlow, is this resizing call that happens in the GAN. So if you were doing this on a real model, you might want to consider rewriting these calls with different similar operations that could use the TensorFlow to go a little faster. Okay, I know we have some work on PyTorch as well, so I'm going to leave it here on TensorFlow profiling. I'm happy to take a question or two before we switch over to PyTorch if there are any. If not, Filippo, please go ahead and take it away.
Sure. Hello, everyone. Hopefully you can see my screen. Can you see?
Yes.
Okay. Right. So as Corey just demonstrated for TensorFlow profiling tools allow you to get a better understanding of your application, and in particular can give you insight about any issue you might have in your code, or where to start from if you're looking to optimize your code. And a naive approach to profiling would be to manually add time functions around bits of code with Python timing functions around your code, and then print out the difference in time from start to end. That naive approach has several limitations, including a lot of modification to your original code, and incomplete picture, because you cannot do this for every function in your code. So profiling tools come to the rescue here and give you a more systematic and simpler way to profile in depth several aspects of your code, not just the runtime, but also other issues like the memory, for example. So in the second part about PyTorch, I'll give you a quick overview of profiling tools that are specific for PyTorch, as well as others more general for Python code, and how those can be combined together. And we'll also demonstrate the TensorBoard interface for PyTorch Profiler. Let's start with, so we run these examples on Polaris. So the first thing I'm gonna do is I will SSH into Polaris and get a node into interactive mode. So I'll just do SSH Polaris. I'm on a login node. I will copy this to get an interactive job. And then I will have to load the Conda module and then activate the Conda base environment. So this environment contains pretty much everything we need to run these examples, except this library that is not installed, and you can use this pip line here to install it locally, and this will go in your home folder in this directory. I have already installed this, so I don't have to do it. Okay, so let's start. We will analyze a very simple piece of code, which is a pre-trained ResNet 18 model from Torch Vision. What we're going to do is to our first example, I can just go to the code here. It's just a few lines. Basic imports, and then we will import this Autograd profiler from Torch Autograd, and then we basically set as default type for our tensors to be double type. We load the model, we generate some random inputs with the right shape, and then we run the model on that input. So the only thing you need to add to the code to profile this is import the profiler, and then use this with profiler.profile as prof context manager to basically profile everything that is inside this scope. You can also use prof.start and prof.stop if you prefer, without the context manager. So then finally we print the results using this print statement, and we specify this argument that we want them sorted by the CPU time total. So I can just do it. So the first thing I have to do is, so I got my node, I got my Conda, and then I move to the folder where I have cloned the repository and the PyTorch profiler folder. So you can do a git pull just to make sure that you're up to date with everything that has been pushed recently to the repo. It's taken a long time. Hopefully it doesn't break. Okay. Then so here in this folder you have 3 folders. We're gonna run the first example. So the profiler now will output this table. This is sorted by the CPU total time. So the overall time is 1.4 seconds. In this table you have the first column is the name of the PyTorch operators that are called, sorted by the CPU total time as we asked. So each operator in turn is called other children operators. And so the total time here include the time of that operator, including all of the children. So it's the sum. If you want just the time spent on that operator, that's on the self CPU. So you see this A10 comp2d, which is the one taking the longest. It's the operator itself is super fast, and so one of each children is the one where the code spent most of the time. So you can see that this is probably, so comp2d calls convolution, which calls the other convolution, then specifically this THN and comp2d, which finally calls this A10 slow comp2d forward, which has self CPU, which is similar to the total CPU. So that means this is the operation where we spend most of the time, and which is natural given that we are this is a ResNet model with lots of convolutions. Other attributes you can use is ask the profiler to group results by input shape. So in this case, what this will do is it would add like an extra column with the input shapes. And so you have several comp2d that are split by the actual shapes. So if they are called with different shapes, they appear in different lines. This can be a way to quickly see which of the shape that you're using is taking the most time, but we'll see later that there are maybe better approaches, such that the one to use labels in order to profile a specific bit of PyTorch code. Another flag, another argument you can use when you print your profiling results is when you call your profiler, is to also ask to profile memory, and then you can sort by memory usage, and this would produce this output with this extra CPU mem column, where you can see which operator allocates how much memory. And in this case, this empty operator is the one that's usually called by PyTorch when it allocates in the initial memory of your tensors. Okay, so a first example of how you can use these tools to identify bottlenecks is, for example, noticing that in our previous example, the operator that was taking the most time, so the one that we should first look at for optimization of the code, was this slow comp2d forward. So now if you Google and do some research about this, you can figure out that of course, this, as the name suggests, is a slow operator, and PyTorch may use a faster one, which is optimized with mkldnn. However, in our specific case, this was not possible because we set the precision to be double precision, and this is not available in mkldnn. So by simply switching from double precision to float, so single precision, and running this again, we can see that this time we have that most of the time is spent on mkldnn convolution instead of the slow conv to the that we had previously, and the total time has dropped by almost half. Okay, so let's now move to another example of profiling, and this time we change our model. We create this model where there is a linear layer, which is in fact a multi-layer perceptron, where we do a little bit of linear operators followed by nonlinearities, and those are concatenated together. And then we do this other operation where we create a mask. So we first use the result of this multi-layer perceptron to compute a threshold, a scalar, and then we pass a mask tensor, and we basically extract all the indices in this tensor where the value is above the threshold. So in order to do this, we first move the mask tensor to the CPU and convert to a NumPy tensor, then do this threshold operation and select the NumPy argware, and then transform this back to a CUDA tensor. So as you can imagine, this is quite ineffective, and we'll show that. So the important thing to notice is that we are using this additional profiler.record functions, which can be used to add labels to the code that's within the this with statement. And here we add a label for the linear pass to measure how long it takes, and one for the masking. We can I can show the code as well. And now we are also using the GPU, and because we are passing the CUDA float tensor types here, what we also do is we call the model once outside of the profiler context manager here, because usually when using GPUs, the first iteration is the slowest, so we want to exclude that from the profiling. And then we do as previously to profile the function. So we can run this and see that we have like the masking part that's taking most of the time, literally like 99.9%. And that's because we just saw that it's moving stuff out of the GPU to the host and then back to the device, and doing NumPy operations on the CPU. So we can fix that doing everything on the GPU, and this example basically demonstrates that it's important to, as much as possible, to stay on the GPU. And so we do this by computing the threshold, which stays on the GPU, and then removing the NumPy calls, and just using PyTorch functions to get the indices that we are after. If we do this, we see that the time is now 3 milliseconds, so a factor of a few hundreds times reduction, resulting from both eliminating the copying back and forth from host to the device, and especially running the hardware on the GPU as opposed to the CPU. Okay, so one potential kind of issue here is that this PyTorch profiler only profiles PyTorch operations, and the NumPy hardware function is not a PyTorch operation, is a NumPy operation. So we just looking at the PyTorch profiler, this is not really apparent. We just know that it's taking a lot of time, in here, but we don't have much detail. So we can use the Python C profile to have kind of a more global understanding of the time taken by all of the functions in our code. Of course, we don't have as much detail on the PyTorch functions anymore. The way to do this is to import the C profile module, and then using again this with cprofile.profile, and then printing results. So very similar to the PyTorch profiler setup. From here, you can see that the slow model with the NumPy hardware operation appears here as kind of the part of our code that's taking most of the time. So looking at this result, we could immediately see that what we had to do to speed up the code was to somewhat change how we were doing the hardware part. A very useful and quick way to get some insights on how your code is doing is to use this Torch utils bottleneck tool that basically what it does is run all of your code without the need to modify anything with the PyTorch profiler and the C profiler. And so you get a combination of the two outputs. So I can also demonstrate this, and I will run this code. You just have to call Python and then your model name, and in between put -m torch utils bottleneck. It takes a while, and we'll print a big output with the result of C profile first and the autograph profiler, both on the CPU and on the GPU. Let me make this bigger. So yeah, you have the first part with this, which is the C profiler, then the CPU, and then the CUDA, where additionally you have information about time spent on the GPU. However, the downside of this is this would profile everything in your code, include warm up and other, maybe data loading that you do only once at the beginning, and can skew the performance. You don't have much control with this, but it's a good tool to get an initial feedback on your an overall kind of look at your entire code. So maybe the most interesting thing that I unfortunately have not much time to go into is the new PyTorch profiler, which is basically super compatible with the autograph profiler, which will soon be deprecated. So to use the new profiler, which will give you exactly the same results, you just have to change the lines as shown here, and you can profile both the CPU and the CUDA activities. The main advantage of using the new profiler is that it's compatible with the TensorBoard dashboard that can visualize your profiling information. And so this is using the new profiler, and where I asks to, whenever the trace is ready, to use the TensorBoard trace handler to save results to a JSON file. And then we can use the TensorBoard plugin to load those. So I can run those examples using Python example 3 v0. So this would save the, so then I can go ahead and start the TensorBoard. Sorry, of course, I have to SSH into Polaris. And then on a login node, I load the modules, activate the conda environment, cd to the correct directory. And then here I should see the two JSON files, results of the profiling operation. Let me also run the v1. And I can then use TensorBoard to, with logd to the current directory, kind of a random port, a number, pick that one pretty high. And then this is starting. In the meantime, I can do a SSH port forwarding to see the results on my machine here, changing the right port. Okay, so I can now go to, and I should see the results. So here I have the two profiler jobs that the two examples I run. And here I have the several spans. I didn't get to explain that. You have several views. This is an overview where you have an overall measure of how well you overlap the code. Well, this is basically the time taken on the kernel versus other operations, and where kernel has the priority. If you overlap with others, it would show as kernel. And usually you want to look at how much you use the GPU, although just looking at this number is maybe misleading, but in general, high number means good utilization. You have then the operator view where you can sort operators by the total duration, and you get the similar results we saw. We can also click in here on this other profiling. We can view the stack, so which lines of code called that operator, and this is in the forward pass and so on. And finally, you can have information about the GPU kernels. So which kernels are used, and you want to possibly check that those that are used more often have a high min blocks per streaming multiprocessing. So if this is close or lower than 1, then you may want to check to feed more tasks to your more blocks to your GPUs. Maybe do a bigger batch size. And you have the trace part where this is something Taylor and Corey showed already. You can zoom in and get a nice, for example, this is the CPU time, and this is the GPU time traces. You can, for each of these, you can understand. So if I go to this one, probably I can click to one of these to get which CPU operator called that GPU kernel. And here you have the GPU utilizations if you want this to be high. Again, finally, you have the memory that tells you again which how the memories are allocated, deallocated in time, and which operator are responsible for each of these calls. So I guess I'm already kind of over time, so I guess we're happy to take questions on Slack.